Good.
Great. Well, good afternoon, everybody, and thank you for spending your lunchtime participating in this webinar for you. So I hope the information that I'm about to go through with you is going to be useful to your projects. We will be taking questions at the end. Tracy's going to host that. A little bit about me. I'm a chief engineer for Titus HVAC. I've been in the industry for about 30 years. 20 of those years I've spent working on air water systems such as chill beams. As you can tell, I'm not from around these parts. I am actually based in Cumming, Georgia, a little bit further north than most of you. But I moved to the USA about 18, 19 years ago to support chill beam technology in the United States. It says here I've got 20 years air water experience. Actually, it's probably a bit more because I did about sort of 3 or 4 years working on the system in the UK, where I'm originally from. But anyway, at the time I arrived in North America, around about 2005, chill beam systems had just started to take off in the country. So it meant that I got involved in some of the very early projects to adopt the system. And at the time, I was working for a German company called known as Trox, who are also based in the Georgia area. So yeah, some of those landmark projects include Moses Cone Hospital in Greensboro, North Carolina, which is the very first chill beam project, very first hospital to adopt chill beam technology for a 24-hour facility. So yeah, that's a bit about me. This is what we're going to cover today. We're going to go over the active chill beam basic operation principles. We won't really be spending much time covering passive chill beams. They really represent only a very small amount of the market in North America. Almost all chill beam projects are the active beam type, so that's what we're going to be covering. They look at the different variants of chill beams, the sort of formats of them. We're going to talk about the design basics in terms of the wet side, the pipework side, and the primary air system, comparing constant volume systems, primary air systems to variable volume. We're going to be looking at controls, and I'm going to make a selection for you as well. And finally, we're just going to finish off with looking at what the system costs are. So the basic operation of an active chill beam is it doesn't have any moving parts. It's served by a primary air system, which is a central air handling unit, which sends cool, dry air across the building via ductwork. Now, chill beams are a decoupled system. So what that means is that the air handling units cover the ventilation and dehumidification side, and the chill beam units themselves cover the sensible cooling and heating side of the system. So that's where it's decoupled. Chill beams are, like I say, sensible cooling only. That means that the chilled water that is piped through these chill beams is held up just above the room dew point condition, and that keeps the coils running dry. So you don't need things like filters and condensate drain trays. So yeah, how it actually works is we're sending this air and pressurizing a primary air plenum chamber at the top here, and this centralized air pushes its way through these induction nozzles. Primary air leaves those nozzles at around about 3,000 feet per minute, and these jets cause a slight vacuum above the coil, which entrains room air across the heat exchange coil, where again we're applying sensible cooling or heating. That secondary air mixes with the primary air and is pushed into the room via typically 2 slots. So from the room side, they just look like sort of wide slot diffusers, really. We should really mention entrainment ratio here. What we mean by that is how much air is moved across the cooling coil, the cooling and the heating coil, versus how much air is supplied to the primary air plenum chamber. So a typical active chill beam selection, you're going to induce up to 4 parts of room air across the coil for every 1 part of primary air you send to the plenum chamber. It's a 4-to-1 ratio. So for every 100 CFM, you're going to induce up to a 400 CFM across the coil. So if you think about it, that's quite a large volume of air that's being moved for very little energy outlay. There's no fans needed to move that air. So it's a very efficient way of moving air across a coil. Now, chill beams use chilled water, as I mentioned, to accomplish the sensible cooling. And water is a far more efficient medium than air to move heat, to move cooling energy. So when we compare it to all air systems such as VAV, it's far more efficient. So a 1-inch diameter water pipe can carry the same amount of cooling energy as a 16-inch per 16-inch air duct. And that is because water is 800 times denser than air, and it has a specific heat capacity of around 3,500 times that of air. So you can see straight away where you're getting some space savings there. When it's one of the things you notice about a chill beam installation is if you put your head up into the ceiling void and have a look around, you see much smaller pipes versus a lot of sheet steel ductwork that you would get with the conventional VAV system. So far more compact. Now, we still need air to accomplish the dehumidification and ventilation from the central air handlers. But that air will also offer some sensible cooling on top of the latent cooling. Typically, we can expect to get about 30% of the overall cooling of the zones, compared to 70% of the cooling will be done with the water. So it's like this 30-70 sort of ratio. So why am I telling you this? Because it's useful to know when you look at air system size reduction comparing to all air systems such as VAV. So if we were to take, for an example, an office building, the typical airflow requirements, we're going to need for the building approximately 0.15 CFM per square foot to ventilate the building. While on the interior zones, to cover the sensible and the latent cooling, we're going to need about 0.2 CFM per square foot for latent cooling. And for sensible cooling, up to about 0.5 CFM a square foot. Now, on the perimeter zones, because the loads are so much higher, we're going to need a lot more, particularly in southern climates like we have in Georgia. So we may need on the perimeter up to 1.5 CFM a square foot with a conventional VAV system, and a bit more for the latent cooling compared to the interior zones because of infiltration. So we may need somewhere between sort of 0.3 and 0.4, something like that for the latent cooling. So the point I'm making is that these areas here, this extra air here that we're using for the sensible cooling, that is where we can eliminate air system size. So as you can see, it's quite vast on the perimeter. We could reduce from maybe all the way down from 1.5 CFM a square foot down to about 0.4 to 0.5. So almost, in some cases, as much as 1 CFM a square foot can be taken out of the system. Now, an active chill beam, as I mentioned earlier, has a very typical air distribution pattern because it's delivering the air through slot diffusers. So the air is thrown across the ceiling, it sticks to the ceiling using the Coanda effect, just like a slot diffuser, until the air either hits another colliding airstream and comes down into the occupied zone, or finds a wall and comes down. So nothing unconventional about that. It's what we call a mixed air system, okay? And that's a typical installation. This is a school commons room where you can see that we've got 2 foot wide, 8 foot long active chill beams. And I think there's 6 of those that are installed there. Very typical installation there. And you can see the spacing here. It's about 8 foot centers, which is quite typical for active chill beams. Somewhere between 6 and 8 foot is quite typical there. Applications, ideal applications for chill beams, office spaces, educational facilities. That's probably the largest market for active chill beams in North America. Owner-occupied buildings, any owner that's got a long-term interest in the running costs of the building, and also the maintenance aspect, that sort of thing. These chill beams are very low maintenance. There's no moving parts, and we can save we get some considerable energy saving benefits over conventional VAV for the right type of application. Not all applications, but for the right type of application, it's been proven to be energy efficient. Some other applications that are growing is healthcare. We're seeing more and more installations in patient rooms, and chill beams can be used to help accomplish the recirculation air changes and still be compliant with ASHRAE standard 170 guidelines. And also laboratories. In fact, labs were the very first major applications to adopt chill beams in the USA. And I worked on some of the very early applications for labs. Anyway, so what we need to know is what applications we need to avoid. And basically that's any building or room with high latent loads, or if the building cannot be sealed very well and the humidity cannot be controlled. But there are some exceptions. And a few years ago, I worked on a project in Nashville, Tennessee. It was an old historic building, which was extremely leaky. And one of the major engineering firms around Nashville was tasked with designing this building. And they found that they couldn't, it was a renovation, and they couldn't change the interior of the building too much because it was a historic building. They found that they just could not squeeze in a conventional VAV system. So they were actually forced down the route of using active chill beams in this very leaky building. And I won't bore you with the ins and outs of the design, but trust me, it was challenging. We had to use super dry air for the primary air to get this system to work. But it did work, and it's been running now for several years. So there is always the exception to the rule. I'm just saying that poorly sealed buildings are not the best application rather for any sort of chill beam system. Some other examples: kitchens, obviously, because you're boiling water there, so high latent loads. Gymnasiums are not good. Wet labs, exhibition halls, those sort of applications, you should avoid using chill beams. So the system design basics here. The first off, we're going to talk about the wet side and medium temperature chilled water loops, heating with the beams and the controls. So as mentioned earlier, we don't want to be putting low temperature chilled water through chill beams. So conventional chilled water that you're all used to, for dehumidification, is around about 43 to 45 degrees. So that's what your chiller usually produces. That's too cold to put with chill beams. Through chill beams, you're going to get condensation if you do that. So what most engineers do is create a secondary closed loop, separated by a plate and frame heat exchanger. That can ensure that there's no accidental way to send 43-degree water to the chill beams. So we set this secondary loop up somewhere between typically 57 to 61 degrees. And as a rule of thumb, for a design, you want to be setting the chill water temperature round about 1 degree above the chilled water the room dew point temperature. That gives you some safety. But the reality is, and many engineers do actually do this, they design right at the dew point, because that is not cold enough to produce condensation on the coils, not even close. Actually, the chilled water temperature needs to be quite a few degrees below the room dew point before the first condensation droplets will occur. But I'm not recommending you design that way. I think a good rule of thumb is just 1 degree above the room dew point and you'll be fine. So somewhere between 57 and 61 degrees. Now, you might notice here that there are 2 temperature sensors on this secondary loop here. The first one is to control the modulating valve that bypasses the plate frame heat exchanger. That's to get your initial temperature control for the secondary loop. But the second one is used as a thermal cutout. Now, what this is designed to do is that if it picks up a low temperature, um, you know, downstream of the pumps, then it will automatically shut the pumps off. It's set, set up to some control mechanism that will close the pumps. And the reason I recommend this is that just in case there's a problem with the modulating valve, if it jams, say in the wrong position, sending too cold chilled water straight to the chill beams, the temperature could start to drop from 57 down to maybe sort of 50 degrees, which could start to cause some sweating on the beams. So this is a thermal cutout, but it also protects that maybe if somebody new to the system, a facilities engineer, decides to monkey with the system and reduce the chill water temperature on the secondary loop, this thermal cutout will prevent that from happening. So I do highly recommend that on all designs. Now, another design that you could consider is an open loop chill water system, which is going to be lower cost than the plate and frame heat exchanger. And what this does is essentially blend low temperature chill water with the return coming back from the beams, which is going to be about 62, something like that, maybe a bit warmer. So you're blending 43 with 62 to give you the 57. Some engineers don't like this because, as I mentioned, there's a possibility that if this modulating valve jams open, you could send low temperature water to the beams. But again, if you've got the safety cutout here, you can prevent that from happening. So I see as many designs with the open loop design like this as we do the closed loop. And I don't think there's any issue with it. Again, as long as you can guarantee that you can control the chill water temperature, either sort of approach would work. But a better approach, if possible, is actually to dedicate a chiller to that medium temperature circuit, because you're going to get a much higher coefficient of efficiency with your chiller if you do that. Far better. But the problem is that you'll need some sort of low temperature method to accomplish the dehumidification. So you may need either a second chiller, or what we could do is use a DX air handling unit to accomplish the dehumidification. So there's lots of different approaches you could take here. And of course, you could tap in this dedicated chiller to groundwater, get some geothermal energy savings there as well, obviously at additional cost. None of these type of approaches are basic costs. There is additional costs here. But again, DX air handling unit, you might want to, for a school example, consider using DX air handling units and a small dedicated chiller to the chill beam loop. It depends on the climate that you're designing the building in and all sorts of other factors like your budget, so on and so forth. And that's to give you an example, actually, what could happen in terms of your efficiency if you do dedicate a chiller to the medium temperature loop. So this is a chiller performance table based on an leaving temperature of 58 degrees. And you can see that the energy consumption is just 0.078 kilowatts per ton. So 78 watts per ton to produce a ton of cooling producing 58 degree water. This is at part load, by the way, but and it's a water cooled chiller. But think about that. That's the kind of the energy almost to power an incandescent light bulb to get a ton of cooling. It's absolutely astonishing. And I've found this with many engineers when they've energy modeled this setup of how much better the system performs energy wise. But again, additional cost. This is some of you may argue getting into a sort of gold plated HVAC system design. But if you're trying to get to net zero, these things don't come cheaply. So I'm going to switch gears now and talk about the zone piping here, and how you may heat and cool with the active chill beams. So in its most basic form, what we could use is to just use 2 pipe coils in the active chill beams and changeover. But I can't remember the last time I ever saw that system design. Most buildings require simultaneous heating and cooling. So we can pretty much eliminate that and then maybe look at a 4-pipe design. Now you just doubled up the amount of pipe work that you need in the zones. and this is one area of active chill beams where the system can get quite expensive, is there is a lot more pipe work than duct work. And depending on the labor rate of duct work versus your pipe work labor, it can skew the cost of the system. So you've got to watch out for this. So 4-pipe systems tend to be quite expensive, but we're getting full simultaneous heat and cooling there. So what a compromise maybe is still use a 4-pipe system, but reduce the amount of pipe work in the zones by actually not using the chill beam coils at all to do the heating, and just heat a duct-mounted coil to heat the air to the chill beams. Something similar to the type of coil that you'd use in a single duct VAV box. So that's one option. We see this is quite a common design, and it saves considerable cost actually on the pipework layout. Alternatively, we could consider using a 6-way valve. Now, this is quite common on a lot of chill beam designs now, but basically we're using a valve that has a flow and return for the hot water, a flow and return for the chilled water, and a 2-pipe out to the chill beams. It essentially converts 4-pipe to 2-pipe. And it looks like this, and it operates like this. Okay, so you can see here, we've got the flow and the return for the cooling, and the flow and the return for the heating there. And this is a common pipe out work at sending either hot water or chilled water to the beams. So at the moment, we're showing the cooling mode. Now, what's going to happen during cooling, that the space temperature is going to be satisfied, and then we're going to go through the deadband to the deadband. So what will happen is a single actuator that's controlling the 6-way valve, so it's controlling both heating and cooling water, will rotate through it to its halfway position, its deadband position. So all 6 valves are now closed. So no water at all is running through the chill beams. Obviously, you've still got your primary air, which is dehumidifying and ventilating the zone, but no cooling or heating from the beams is occurring. Now, if you've got a demand for heating, the valve will rotate from its halfway position and modulate up to full flow through the heating. So this can be modulating, or you could actually set the valve just to run in 3 positions: fully chilled water, fully closed, so deadband, or full hot water, 3 positions, or modulate. So either or. Anyway, so this is flowing the hot water through the chill beam. So now we're heating. Now, one of the primary considerations you have to think about if you're going to considering using 6-way valves is water treatments. What you'll notice here through this setup is that the water mixtures between the hot and the cold side must be the same, because they will mix. So if I run through the cycle again, let's say you've got glycol running with the chilled water. So what we're going to do now is go through this cycle of cooling. We're pumping chilled water with glycol through the chill beams. And then as we go through to the deadband, we've still got glycol in the circuit of the chill beams. And then as we switch over to the heating, you'll see that the glycol that was in those chill beams from the chilled water will pass back through the return of the hot water. So if you're using separate treatments in the chilled water versus the hot water, you cannot use 6-way valves for this application. You'd need to go back to the duct-mounted heater or even 4-pipe chill beams. So that's the downside of a 6-way valve. But they do save even more cost compared to doing the duct-mounted heater, because you've only got now one single actuator controlling both the heating and the cooling, and reduced pipe work. So it does save system cost. So let's switch over to talking about the primary air system now. So the first thing we should consider is actually how much primary air the chill beam system requires. And it's going to be the greater of the following 3. Okay, first off, how much air that we require for adequate space ventilation. So that's going to be determined by ASHRAE's standard 62 calculations, or the guidelines laid out for healthcare, the standard 170. Also, the next aspect to consider is latent cooling, so building humidity control. So we can calculate that by using this formula here. I'm not going to run it through it with you. There's no need. But that is the formula to calculate how much airflow that we need to offset the latent gains in the space, the people gains and the infiltration. Now, one of the tricks I should mention at this point that we can build into these calculations is we can consider the room design condition in terms of relative humidity. We're all used to designing buildings to 75 and 50% RH during summer. That's the most common design condition. Now, this statement I'm about to make may surprise you, but actually with chill beams, it does make sense to move the humidity design up slightly. ASHRAE guidelines, approximately for 75 dry bulb, you'll see that for comfort, that your RH can be somewhere between 50 and maybe as far up as 60. But what you'll find is that if you just nudge up the RH design point up to about 53 RH, maybe 55 RH, it makes a dramatic difference on how much primary air that you need to cover the latent cooling. So it reduces the size of the air system, or it reduces the expense of the air handling unit that you may consider to produce dry air. So when we plug a slightly higher RH into this formula, obviously we've got to convert it to grains because we're doing W primary air and W room. So at this aspect here, if you just plug that into this equation, you would be surprised how much difference it makes. So if you move from, say, 50 RH up to 55 RH, you may be able to save as much as 40% air in terms of CFM to the space. Most engineers that nudge this up, this RH up, stick to maybe around 53 RH and don't go above that. And that, again, makes quite a significant difference. So finally, the greater of these three would be the primary airflow rate required to drive the space sensible cooling. What that means is how much air above the ventilation and dehumidification you need to push through the nozzles of the chill beams in order to induce enough room air across the coil to cover the sensible cooling. And on the perimeter zones, that primary air, that last one there, can be double in some cases what you need for these two here. So if you maybe need 0.25 to 0.3 CFM a square foot for your latent cooling, you may need sort of 0.4, 0.5 CFM a square foot if your loads are extremely high. But again, still, you're getting a huge reduction compared to conventional VAV. But the reason this is an important point, because it may dictate the type of air handling unit that you use. So you may be forced on the perimeter of the building to either over-ventilate if you're using a DOAS system, DOAS air handling unit, or what most engineers do is use a recirculation air handling unit, so they don't go DOAS at all on the perimeter. But this really mainly applies to office buildings, because office buildings have much lower ventilation rates compared to some other applications like healthcare and classroom applications. Classroom applications, you'll usually find that these three items that I've listed here, what drives the primary airflow requirement is actually the first two. So the ventilation and the dehumidification. So in other words, you don't need any extra to push through the chill beams to get them to cover the sensible cooling. But office buildings on the perimeter, it's more complicated. So just bear that in mind. So for that reason, you may be using a recirculation air handling unit, and which is this type of air handling unit here. This is the type of thing you may use on an office building. So not DOAS at all. So we're going to mix return air with outside air, push it through the cooling coil there, and send the air to the building, maybe at 52 degrees saturated. Just going to pick up some motor heat and some heat from the ductwork. That is about as warm air as you're going to get away with on an office building. Ideally, you may be wanting to drop below, a little bit below 52. But for this setup that I'm showing here, you would, for most designs, you'd probably want to be designing the office building at around 53 RH to get away with that. Now, you could use a DOAS for some applications, maybe a school application. So this is the kind of setup that you use there. But one thing to note, though, that this cool 52, 53 degree air, if for a high ventilation rate application like classrooms and patient rooms, then this may be too cold, and you may end up with reheat issues, parasitic reheat. So for that reason, many engineers design this type of air handling unit for those type of high ventilation rate applications, where they use a secondary wheel to warm the air back up. So basically some sort of heat recovery. So what you're doing here is swapping sensible heat for latent heat. And what we're doing is drying the air downstream of the cooling coil, but also dropping its dew point. So you end up with very dry but warm air. So you may consider this type of thing for healthcare. For classrooms, I don't think I've got a slide on it for classrooms. No, I don't. But for classrooms, you may want to consider using a DX air handling unit with hot gas reheat. That will reduce the amount of potential reheat in the shoulder months when you're trying to ventilate the classroom. So lots of things to consider here on the air side. So anyway, moving on to controls here. There's various different ways you can control the airflow, but I've just categorized it into constant volume and variable volume. Most chill beam systems are designed constant volume. So what we basically do is just vary the chilled water flow to the chill beams and keep a constant primary airflow rate. This is a good design because it helps save with system costs. So you don't need VAV boxes upstream of the chill beam units, essentially paying for two systems. So I'd always recommend consider using constant volume air before variable volume. But if you do variable volume, you may consider using variable volume on the perimeter of an office building and have some VAV boxes upstream of the chill beam units, which is set back during the shoulder months to run a 50% airflow rate. This is going to save energy and limit overcooling on those perimeter zones. But obviously the controls are going to be more complicated because you've got to schedule both the airflow and the chill water flow with your digital controls there. One thing I didn't mention is that in both of these examples here, I've shown modulating water flow to the chill beam coils. You could do simple on-off valves, just two position. That's perfectly okay. And that can, again, save some cost on your system design there. So just sort of comparing constant volume versus variable volume, I've just done some pros and cons here. Constant volume, lower cost, better humidity control, because this is something else you'd have to consider if you use variable volume with upstream of your chill beam units, is that once you start to modulate the airflow down, you're losing some of your humidity control. Because remember, your primary air is your sole source of controlling the building humidity. So you've got to consider that. So constant volume is really suitable for lower primary airflow rate type applications, like interior offices, that sort of thing, and also to lower load type of applications. Variable volume is obviously higher cost, more controls required, and more control programming required. And you need to think about scheduling to control humidity, that sort of thing. But these are sometimes used in perimeter office buildings, with very high loads. So lots of floor to ceiling glazing, that sort of thing. Maybe schools, educational facilities, and generally higher load applications. Now, one of the easiest aspects really to talk about when we talk about controls of chill beams, believe it or not, is condensation control, because actually you don't need very much. A lot of the early projects that I worked on in the early sort of 2000s was they had all sorts of controls to monitor humidity and pipework sensors, that sort of thing. But really, all you need to do is floor dew point monitoring. So a small number of dew point sensors across the floor connected to the BMS, which then will adjust the amount of dehumidification that either the DOAS or the mixing air handling unit needs to do. So there's your decoupling there. So we're controlling the building humidity separately from the zone control. Okay. So if you do have operable windows, you could use a zone control valve connected to the to the BMS and a dew point sensor. So what happens is the windows are open, then the humidity in the room rises. That sensor picks that up and basically sends a signal to the BMS to close down, to the controller rather, and stop the water flow. That way, that prevents any sweating on the chill beams. And what will happen is obviously the room will start to warm up, and the occupants will learn to close the windows. And then what will happen is obviously the system will get back into control because you've got your primary air is still running, and you'll get back into control, and then the chill water valve will open as soon as the room is under control again. But these type of sensors, I mentioned those just a little earlier. They're not really required. They tend to be too sensitive, and for several buildings I know of, certainly in the early designs, they actually had to rip them out because they were just so sensitive. Because it's normal to expect a slight bit of misting on the chilled beam supply coil. So strapping these to each chill beam is going to add a lot to the cost of the system, and quite frankly, they're unnecessary. So what I'm going to do now, just to finish off the last sort of few minutes, is just to talk about the chill beam selection process, how you actually select one here. It's a 5-step selection process. The first thing you need to do is choose your design parameters. So things like your primary air temperature, your room set point temperatures, chill water temperature, hot water temperature, that sort of thing. Then what we do is we can paste in the cooling and the heating loads straight into the Excel selection tool, which I'm going to very briefly show you in a moment. And then it becomes very easy. It's an automated process. We just choose the aesthetic style of the chill beam. Typically you choose either a 12-inch wide or a 24-inch wide active chill beam unit, and then decide what quantities you're going to use in those spaces. The chill beam selection software suggests quantities for you, but you can choose to use those or just enter in your own quantities that you choose for the space. And then you simply press the rapid select button. So just a little tip here: when we extract the zone loads for the chill beam system design, we're interested in just zone sensible loads. So that's in that column there. And obviously your latent load, by the way, because this selection software will work out how much air that you need for your dehumidification as well. That can be done with this. If you look here on your people load, you've got your net total and you've got your space sensible. So you can subtract one from the other to get your latent loads. Okay, so that will give you 4 columns of data, basically your ventilation rate that you need for the building, for the zone rather, your sensible cooling load, your latent cooling load, and your heating load, which comes from here. So yeah, and there's your airflows there. So you pull all that out of your zone checksums there. To click it, you'll need some Titus software. The team software, you click on the chill beam project button, and up pops this. You can see the selection software there. As I say, it's an Excel spreadsheet based tool with some Visual Basic routines running on it. It's pretty sophisticated, and as I say, I'm going to do you a demo in the moment, but this slide is in the wrong position here. But you're going to be choosing from one of several chill beam types, and these are the most common variants. There's a 24-inch wide linear beam on the left there. This unit has the highest cooling capacity of all of these. So it's the most common unit by far that you see on projects used these days. There's a 12-inch wide version, which is also 2 linear slots, offers about a 20 to 30% lower capacity than the one on the left. And then you've got a modular beam, which throws the air in 4 directions. So this beam at the bottom, you typically use 4-way. You'd use that for smaller spaces, like, maybe a 10-foot, 12-foot office space, private office space, that sort of thing. These linear beams up the top here are available in lengths anywhere from 2 foot all the way up to 10 foot, the most common being about 4, 6, and 8 foot. So let's see if we can do an example here. So what we've got is, this is a real example. It's a building that I worked on many years ago. It's in a university, higher ed application, obviously, technology innovation space, 561 square feet. It's got a sensible cooling load of 20 MBH. Most of that's equipment. Latent cooling load of 1200 BTUs. So the occupants here there's 6 occupants. So using my ASHRAE 62.1 calculations to work out the ventilation rate, I need 64 CFM. My room design conditions, I'm going to work to 75 for summer with 53 RH, as mentioned earlier, and primary airflow, my primary air conditions rather, I'm going to be working at 55 Fahrenheit and 48 grains. Chill water temperature, I'm going to choose 57 here. So I'm just going to run this selection here. You'll see actually that I've pre-populated the software with all these loads. So in fact, I didn't mention this, but there's no heating required here because it's interior space. So actually, we've only got these 3 columns here that you need to enter: sensible cooling, latent cooling, and ventilation. Putting in the square footage is useful because it helps calculate how many chill beams you need for this zone. So if you've got that information available, put that in there. So each one of these rows on the software represents a unique zone. So what I'm going to be choosing is the Titus model CBL24, which is the dual slot version, 24-inch wide unit, which has the highest cooling capacity. So this software is suggesting that I use 3, that's in that column here, 3 active chill beams. And I'm going to choose to use that, and I can just press the use button to use the suggested quantities. That will overwrite the manual quantities in that column there. And what you'll notice is as soon as I've entered all this data, it turns green on the far left column. And that indicates that it's ready just to run the rapid select, the automated selection procedure. So I just click that button there, and then we now have a selection. So what we need for this are 3 8-foot long beams. I'm choosing 2 pipe. It does say heating and cooling there, but there's if you put 2 pipe cooling in there, that's more suited because we don't have a heating requirement there. So it's chosen a 2-way throw, B2 nozzle. So that's a medium-sized nozzle. We need 70 CFM per chill beam, which is a total of 210 CFM for the entire zone. And as you can see over in the zone performance, where all of those 3 chill beams together is producing 19.8 MBH of cooling, and we need 19.6, so just slightly over. So there you go. That's really is as simple as that. Now, what I will demonstrate is this, going back to this discussion earlier about relative humidity. So what this is doing is it's basically calculating that I need 210 CFM to drive the chill beams, cover the latent cooling, and cover the ventilation rate. The ventilation rate is only 64 CFM. But what happens if I were to put a very high latent load into that zone? If I put 4,800 BTUs of latent load, you'll see we get all these reds turn up now. It's saying that I need much more air than the 70 CFM per beam to cover the latent load. So all I need to do is just rerun a rapid select single zone, and it will correct that for me. And now I need a whopping 360 CFM to cover the latent load and the sensible load in the space. But watch what happens if I adjust the room RH design conditions. If I went back to, say, 50 RH, conventional design conditions, you'll see that I now need more than the 120 CFM. I now need 137 CFM to cover the latent load because I've chosen a 50% RH design condition. So again, I just rerun rapid select single zone. It will correct for that. So I've now gone up to 420 CFM. So that gives you an idea that you can demonstrate that you can save, you know, primary airflow rates if you design to a slightly higher RH. Going back to, if I go to 55, we select, that drops it even further, and I'm down to 300. Now, what I can do, just a quick demo, is I can actually design a whole building and select a whole building of chill beams in one go by just taking some sensible loads, latent loads, etc., from a spreadsheet, and then just doing a paste straight into the software like this, filling down all my model numbers here, my model types that I've chosen, like this, and the slot types, I'm going for 2 slots here and 2 pipe, just fill those down. Excuse me while I rush this. And again, I'm going to just go with the recommended quantities, and then I can do actually rapid select all zones, and it will run through and select all the units, as you can see there. I'm not going to run through all of these, by the way, just to save time, but you get the idea. You're able to run this rapid select and do an entire building all in one go, and also model different parameters. So what it will do, it does have a summary. There's one of the tabs below here will give you, if you click on it, will give you the building summary. So that will tell you things like how much total primary air that you need for the entire building, those kind of statistics. So you can model different parameters, like, you know, different chill water temperatures, different primary air temperatures, until you come up with the right thing, so very quickly, so you can run these little models. So I'm going to break out of this and now go back to the slides and show how we would, if you remember, I selected 3 chill beams for this application example here, for this technology innovation space. So that's what happened here. That's the end results of the selection, which I just showed you. And I'm just going to lay these 3 chill beams in 3 rows here. And what we can do is space these out equally, and we can measure the dimensions between the chill beams, the center lines, and then plug that into the software, and it will actually calculate what the air velocities in the occupied zone are to make sure that we've selected to meet, you know, our comfort guidelines there. So that's basically how you do that. Other positioning, on just to give you some examples, 4-way throw beams, the modular type units with 4 active slots. You try to position those in the center of the room, although remember, it may clash with lighting, so you've got to think about that. In a hospital patient room, we tend to put the chill beam above the bed, so we don't blow high velocity, chill beam supply air directly down the bed. Again, you've got to coordinate this because you may have radiant panels above the bed, so you've got to think about that, but that's typically where you may put them. In switching over to laboratories now, there's 2 places you can place the chill beams, lay out the chill beams in the laboratory, either over the aisles, which I've shown here, or the benches. The benches are shown in these red rectangles here. So aisles or benches. There's pros and cons of either. You've got to watch for hoods as well, by the way. So you don't want to blow air directly down the sashes of these hoods here, because you could interfere with safe operation. So aisles, if you place them over the aisles, it's easy to get to the chill beams for maintenance by dropping the face and to expose the coil to clean it. Over the benches, it is one option as well, because then you're colliding the cool air between the occupants that are located in the aisles. So either or I've seen with labs. Placing chill beams over the freezers in a laboratory, the freezers generate the heat. So if you put the induction coil and the cooling coil directly above the freezer, you're going to capture that heat directly. So that's also a good thing to consider. So finally, just on cost, before we take any questions here, and again, I'm running out of time there, so I've got to be real brief on this, but this is an example of an office building. It was the headquarters for HDR engineers. It's Omaha, Nebraska, and it's a nine-story office building with one retail floor. And basically what they did was eliminate from the construction an entire floor by using the chill beam system, and that reduced the construction costs dramatically. So what they found was that the chill beam system, there was an 11% increase on the first costs for the HVAC system, which you can see there. But there was a 71% space reduction. So they could free up that space for lettable office buildings. So basically what they found was that the construction cost saving by using the chill beam, by building the building shorter, one floor shorter, the construction cost saving was about 8 million. And then you've got to take off your premium for your chill beams, which is $1.2 million. So you've got a total saving using the chill beams on the overall project was about $6.8 million. But obviously you can only do that if it's a new build. You can't do this with renovations, and you've got to be working with the architect to make benefit of these cost savings that you get. So again, I think that's it now. I think we can open the floor. Tracy's going to take over now and take the questions. But just one final thing, actually. If you do want to see how to use it, if you want to see a tutorial showing you how to use this software, there's a link here. We will be sending a PDF of this presentation out to you. So you just click on this link and it will show you how to use that chill beam software, that Excel sheet that I just very briefly ran through with you. So Tracy, I'm going to hand it over back to you now.